So let us recall what we discussed yesterday. You see, we have record today. So we introduced sound waves and some longitudinal waves, means that particles of the medium oscillate in the direction parallel to the direction of spreading the wave. And we um, made a statement that it's more practical to measure change of pressure instead of displacement because that's something what we can measure easily. So we were trying to find the relationship between wave functions for um, displacement and for pressure change. So we found that they are similar, however, in opposite phase. So there is a pi phase shift between them because one is described by cosinus, another by sinus. So we also introduced speed of sound in different mediums. So what is the equation which we have there? It's square root of bulk modulus divided by density, like bulk density of the. So again, it can be generalized to different systems, different waves. No matter what kind of waves we deal with, we always, when we want to determine the speed of sound or speed of some wave traveling along the string, we will consider in numerator the elastic properties of the medium, and in denominator like inertial features of the medium, means either linear density or bulk density. Also, we determine this bulk modulus, which is not quite common parameter. And from this equation for velocity, speed of sound, we substituted bulk modulus in the expression which relates displacement and change in pressure, and could express change in pressure in terms of density and speed of sound instead of bulk modulus. And that is more practical because we can easily measure density and speed of sound, and these parameters are already known for most materials, so we can readily use them. So today we continue with our work on understanding better sound waves, and we will derive equations for intensity of sound wave, and also consider the common units for measuring intensity. So it's called sound level, which is measured in decibels. So we will figure out why we introduce this and how we deal with this. Right. So let us start with sound intensity. So we consider some model system. Again, it will be a cylinder with a piston, which vibrates with certain frequency. So it provides this energy to the air inside the cylinder. So we have this small element here of air with some mass dm. And as a result of this piston vibration, this element also experienced some displacement in along axis x. So now we want to determine power, which is transferred through the cylinder and provided by this vibrating piston and um, transported through the cylinder. So power is equal, by the way, what is definition of power? What is this? It's work over time. That's rate of work done by in this case by this piston. So that will be force times dot product force vector and velocity vector, and we can consider like velocity vector of this element of air. And what will be force if we know pressure? So we know pressure, we multiply by area, and area, so this, if we consider this cylinder, that is a area of the cross section of this cylinder. So then, taking all this into account, we can write for power that is delta P, change in pressure, as a function of x and t. So this wave function which describes pressure change in sound wave times area times unit vector I along axis x, and then we have dot product with partial derivative over time of wave function which describes displacement of this air element times I vector. So if we consider at given position x constant and take first partial derivative of displacement over time, it will give us this speed, like velocity vector. So this multiplied by unit vector I. Since force is parallel to velocity vector, we can proceed further and consider our previously derived equations which relate the change in pressure with displacement. So we can write here density times speed of sound, but don't confuse this speed of sound with velocity vector, because velocity vector we consider for vibrating small element of air, and speed of sound is just a parameter which is a feature of the medium where sound is traveling. Then we have angular frequency times area times S maximum sinus omega, no, we have kx minus omega t. So that stands for the change in pressure as a function of position and time. Then we have another term here, which is the d over dt. And here we have a wave function for displacement, which will be S maximum times cosinus k x minus omega t. So now let us take this derivative. We eventually get rho times v times omega times a times s maximum times sinus kx minus omega t times derivative, first derivative will give us omega s maximum times sinus kx minus omega t. So we have two sinus here. We eventually get rho times speed of sound v times omega square times area of the cross section of this cylinder times S maximum square, so the maximum displacement of the element of air, times sinus square kx minus omega t. So that is our expression for power, which goes through like any position x at any moment of time. So we have this function. And you see here that we have also frequency and displacement in second power, which correlates with our previous derivations for the wave traveling along a string. We also had this power transported by wave proportional to frequency and displacement in second power. So now let us consider make one more step further, because usually we deal with sound intensity, not sound power. So we want to go to intensity. What is the difference between intensity and power? They are definitely related, but power also depends on amplitude. So it actually is the same, but so power is rate of work done or rate of energy transfer, and intensity is rate of energy transfer per unit area. So we normalize it to unit area. So uh, but in order to get intensity, we need to get average power per some interval of time. So uh, we can consider any interval of time, but makes sense for such periodic processes to consider a period of this sound wave. Uh, and that average we will determine at some given position. So we can pick up any cross section in this cylinder at some x fixed, and determine what will be the average power transported, means energy per unit time transported through this cross section. Um, and for convenience, we can pick up any x, but for convenience, let us pick up x equals 0, so it will reduce the equation. So we will get power at x equals 0 will be rho times v times omega squared times s maximum squared times area times sinus square. Kx will be 0. It will be minus omega t. So that's the function which we are going to work with. How if we have some function f as a function of, let's say, some x independent variable, and we want to get average value of this function in the interval from a to b. So the general equation is the following. It's 1 over b minus a times integral from a to b of this function dx. So we will just consider this function instead of f versus x. Um, you see here that this is just some coefficient which is time independent. It doesn't change over time, so we don't care about this coefficient. It will stay like this when we go from instantaneous value to average value over some time interval. What we do care about is this part, sinus square uh, minus omega t. So let us write it down here, sinus square minus omega t. And here we can mention that sinus minus x will be equal to minus sinus x, and sinus square minus x will be equal to sinus square x. So we can, instead of this, consider sinus square omega t. Now we need to determine what will be the average of this function. over time interval which corresponds to the period of the sound wave. So sinus square omega t, let's say average for, maybe we can specify it from time 0 to time t, that will be equal to 1 over t integral from 0 to t sinus square omega t dt. So in order to get this integral, we need to recall that sinus square alpha can be represented as 1 minus cosinus 2 alpha divided by 2. So we can split this integral in two components, and that will be the following: 1 over t, 1 half integral from 0 to t dt, minus 1 half integral from 0 to t cosinus 2 omega t dt. So what do we get? For first one, it will be 1 over t times t over 2. Then minus, and here what we need to do, we need to divide it by 2 omega, and here multiply by 2 omega. So we have the same argument of the function as the differential. And we get 1 over 4 omega sinus 2 omega t from 0 to capital T. That will be here, we cancel this out, so it will be 1 half. And for the second term, we get minus 1 over 4 omega sinus 2 omega times capital T. So tell me, please, what this guy will be equal to omega times T. Lambda? No, I mean the sinus of these 2 omega T. So what is omega? How we define omega? Omega will be 2 pi times frequency, or as you mentioned, 2 pi over t. Now, what do we have for product omega times t? That will be 2 pi over t times t. That will be 2 pi. And sinus of 2 pi will be equal to 0. So in this case, we have just 1 half. So that is the average of this function in the interval of one period of the sound wave. Now we recall what we had before, like this coefficient, and we just need to multiply by 1 half, and we get the average of power transported through x, like cross-section at x equals 0, in the time interval from 0 to capital T. So we can write here power average will be equal to 1 half times rho times V times omega squared times A n times s maximum square. So that is the average power. And mm, next step, we want to get to intensity. So in this case, we divide this power by area because we need to normalize it per unit area. So intensity will be power average divided by area, and that is 1/2. Then still the medium, speed of sound, omega square times s maximum square. So now we have the intensity of sound wave in terms of the displacement of the element of medium of air. So that is not very practical because we don't measure displacement of air particles. We deal with change of pressure. So we recall that delta P maximum is equal to rho times V times omega S maximum. From here, we can express this product. So it will be omega times S maximum square will be equal to delta P maximum divided by rho squared, rho squared times V squared. Now we substitute it here and get intensity in terms of change of pressure. It will be 1/2 rho times V times delta P maximum second power divided by rho square times V square. We cancel out these guys. Will give us delta P maximum square divided by 2 times rho times V. So that is the expression for uh, sound intensity, which we derive in terms of change of pressure, which we can measure in any point. And we considered so far a cylinder as a model system. So in that case, if we don't take into account attenuation of sound with distance, so we consider some small distances, doesn't matter which cross section we pick up, x equals 0 or x equal like 5 centimeters or whatever. This will be, intensity will be the same. However, that is some specific example. Usually we deal with point sources of sound, and then the sound waves possesses spherical symmetry, so it spreads from this point source in all directions, and this factor should be taken into account. So if we consider a cross section of this sphere, just half of it, so we get some arcs like this. This is our point source. And these lines, they correspond to so-called waveform, like wavefront. And wavefront is a geometrical set of points which possess the same phase for wave. So all these points here on the wavefront, they possess the same phase. The distance between these lines, which like arcs, which denote a wavefront, is wavelength, lambda. And if we draw some like radial lines, which are always perpendicular to the wavefront, these are rays, so-called, which define the direction of sound wave propagation. So if we have such a point source and we know its power, like some average power, then also intensity, as we know, it's average power divided by area. However, in this case, obviously area will be a function of distance of this radius from the point source to the point where we want to determine sound intensity. So that will be average power divided by 4 pi r squared. So that we need to take into account that if we deal with this model system cylinder, then intensity, like average power is always divided by a fixed area, which is cross section of the cylinder. But with point source, it increases quite rapidly with distance. So intensity will drop quite uh, significantly as we go further from the point source of the sound. So now, when we already derive the equations and introduce the um, concept of intensity of sound wave, the question will be, why don't we stay with units for intensity of sound wave, which are commonly used for intensities? And by the way, who will remind me what will be units for intensity? Power per area. So power is what? Is work per second. So a joule per second. What then? There is a special unit for that. It's watt. And then meter square. That is unit for intensity. Generally accepted. So the question is, why do we need to complicate our life? And instead of using this commonly accepted unit, we invent sound level, which is a new way to measure sound intensity, and is measured in decibels. I'm sure you're familiar with this because everywhere where this sound is measured, the intensity is measured, usually their sound intensity is not represented in watts per square meter, but instead we have sound level. So we cannot say that sound intensity is measured in decibels, it's wrong. Sound level is measured in decibels. Sound intensity is measured in watts per square meter. But everyone is using sound level. So the thing is that there is a very broad range of sound intensities which can be detected by human ear. So, so we can hear, there is such a term as threshold hearing level, which is determined at 1000 hertz, and that is like I naught 10 to minus 12 watts per meter square at 1000 hertz. So we will later mention why specifically 1000 hertz, but this is the lowest intensity of sound wave which can be detected by human ear. And obviously we can hear like more intensive sounds, and intensity of about 1 watt per meter square, that would be already painful experience. So that will be too loud for normal listening, this sound. So that will be pretty much the range, because it doesn't make, of course you can create sound with higher intensity than 1 watt, but doesn't make sense, because if it's already painful, no one will listen to this. So this is quite wide range. We see it's like 12 orders of magnitudes, and that is not convenient to operate with such wide range of values. In order to avoid this, was introduced sound level, which is denoted as beta, equal to 10 times decimal logarithm of the ratio between sound intensity, sound level of which we want to determine, to this threshold sound intensity I naught. And that is measured in decibels. So let us consider what we get here when we deal with these numbers. So sound level for this already painful sound intensity. So it will be 10 times decimal log. Here will be 1 over 10 to minus 12. Oops. Minus 12. And that will be 10 times decimal log of 10 to 12. So what will be this? Decimal log of 10 to 12. What will give us? 12. And 12 times 10, it will be 120 decibels. So this is the considered to be the maximum reasonable sound level, which still can be normally detected by humans. Otherwise, it goes higher. This one is already considered to be so-called like painful level. So if, for instance, we deal with the absolute minimum with what we can hear, so it will be 10 times decimal log of 10 to minus 12 over 10 to minus 12. It will be 10 decimal log of unity, and decimal log of unity will be 0, so we get 0 decibels. So you see here we change for real sound intensity. We go from 10 to minus 12 to up to 1. And for sound level, we go from just 0 to 120. And of course, it's much easier to operate with narrower range. That's why pretty much always where you see any measurements of sound intensity, they are carried out for sound level and shown in decibels. So of course, if it's necessary, knowing decibels, knowing this threshold level of 10 to minus 12 watts per meter square, you can always go from decibels to um, watts per square meter. But usually always decibels are shown. Another thing what we need to discuss, as I mentioned previously about this 1000 hertz. So let us plot sound level versus frequency. So we will have log scale here. So it will be here maximum 120 decibels, and here will be something like 20. Here maximum will be 20 kilohertz. Here is 20 hertz, and somewhere here will be 1000 hertz. So there is so-called curve of like hearing curve, and it will look something like this. So you see that it has minimum around 1000 hertz, means that is the minimum sound intensity which we can hear. So there is some frequency dependence of sensitivity human ear. Usually we can hear only from 20 hertz to 20 kilohertz plus minus. But the human ear is designed in that way that the highest sensitivity to sound is in this range of in the vicinity of 1000 hertz. Means that at this specific frequency we can hear the lowest sound intensity. And that corresponds to this 10 to minus 12 watts per meter squared. So that's the absolute minimum what we can hear with just without any equipment. And as we go to higher frequencies, this minimum hearing level increases. So in order to, if you still can hear 10 to minus 12 at 1000 hertz, then at, I don't know, 100 hertz, you need a lot higher intensity in order to hear it. The same goes for higher frequency. Um, However, there is one feature of our air that if sound intensity or sound level is very high, let's say close to 120, um, doesn't matter what frequency of this very loud sound is, um, our ear suffer equally for any frequency. So that already doesn't work. So this curve here is only for very, actually it highlights the lowest sound intensity or sound level which we can hear at any frequency. But if sound level goes to the maximum, then doesn't matter which frequency, it's equally painful. So let us summarize our discussion for today. We continued uh, this topic of sound waves, and during today's discussion, we introduced power, which is transporting through the cylinder filled with air at any position x, at any cross section. We determine average power per some interval of time because it kind of doesn't make sense to stick with instantaneous power since it changes non-stop. So we want to get some average power per period of sound wave. And after having this average power, we can go to intensity, which is power divided by area. In the case of this special model system, we deal with area of the cross section of the cylinder. If we deal with more realistic example, when we have point sources of sound, we divide it by area of the sphere with radius, which is the distance between point source to the point where we want to detect and determine sound intensity. So we do not stay with units watts per square meter because the range of intensities which can be detected by human air is very broad, goes from 10 to minus 12 up to 1 watts per um, square meter. And instead, we introduce this sound level, which is measured in decibels. And in this case, the range reduced quite a lot. It goes from 0 to 120 decibel. Of course, it can be higher, but usually not perceived. So also don't forget that human air is not good at equally good to detect different frequencies. So the highest sensitivity is at 1000 hertz. So if you want to annoy maximum level your neighbors with fixed power, then you need to tune it to 1000 hertz, will be heard the most. Thank you very much for attention, and have a good time for this prolonged weekend. We will continue on Wednesday, and there we will start a new chapter, like topic of our course will be thermodynamics, like molecular physics and thermodynamics. Okay, have a good evening. Bye.